Assalamualaikum and good morning to all my students. Okay, for this session, I would like to continue my lesson. Okay, this is about moment distribution method. For the previous video, I have made 4 parts of a video regarding moment distribution method analysis of beam. Okay, so I will continue the beam analysis. Okay, today I would like to share with you how we want to consider the support settlement effect, okay, in the beam. Okay. Okay, let's go through together for a revision session. Okay, moment distribution method. Okay, the learning outcome. Okay, I have explained to you the keyword, the member stiffness, the distribution factor, the carryover factor. Okay, and we have done the analysis for beam. Okay, and then I have also explained on the moment distribution and how we solve the member and forces. Okay, for beam, and then I have also discussed with you how to draw the bending moment diagram. Okay, bending moment diagram using the moment, the end moment that we get from the table, the distribution table. Okay, so of course number 4, you should be able to having technical competency and ability to apply moment distribution method. Okay, okay, the next one is okay. Okay, we have covered number 1. Okay, number 1 means for beam analysis. Anyway, for this session, I want to cover a bit about the settlement effect. Okay, and after that, in the next session, I will continue with analysis of non-sway frame, and followed after that is the set sway frame analysis. Okay, I want to skip this because I have explained this quite detailed in my previous video. Okay. Okay, so this is for the K, the stiffness factor for internal member and for end fix. K is equal to 4 EI over L, and for end pin is 3 EI over L. Okay, I will prepare another video considering the end pin or roller to consider this formula and see what's the difference between 4 EI over L and 3 EI over L. Okay, so this is another formula for stiffness factor. We have K equal to 2 EI over L for the center, the center span. Okay, the symmetry one. Okay, and another one is 6 EI over L for okay, like this for the beam like this. And normally we can cover all analysis in beams using only the first 2 stiffness factor formula. Okay, so in the analysis we don't use the formula number 3 and formula number 4. Okay, so this is the joint stiffness factor or total stiffness, and this is distribution factor, where distribution factor is equal to K divided by total K. Okay, we have gone through this. Okay, so distribution factor is equal to 1 for pin or cantilever end, pin, roller, cantilever end, including all the internal support. Because the total must be equal to 0, except for end fix is equal to 0 because we have to divide by infinity. That is why only fix equal to 0. Okay, we have to divide by infinity like this. Okay, for end fix. Okay, for the carryover factor, we don't calculate the factor, but we use the factor. Okay, for my previous example, since all is fixed, all n is fixed, so we only consider the case where the carryover factor is equal to 0.5. Okay, but for n pin, cantilever and roller, the factor is equal to 0. Okay. Okay, the procedure. Okay, we revise back the procedure, the moment distribution procedure. Step number 1, we have to determine K. Step number 2, we have to determine distribution factor. Step number 3, not determine, we use the carryover factor. We just use the carryover factor. But we don't calculate. We don't calculate the carryover, but we use the carryover in the table. Okay, then we okay, step number 3. Okay, we ignore this step first at this level. We move to step number 4. We have to calculate the fixed end moment, and then once we have determined the fixed end moment, then we will start distribution table. We will start to build distribution table, and we will start the moment distribution. Okay, after fixed end moment, then we have to start moment distribution. Okay, in the table. So in the table, then only we use the carryover. Okay, the process will be doing repeatedly. Start from the first moment value, which is from fixed end moment. Okay, and then carry over. Okay, do carry over. So this is the example given in the notes. Okay, you may refer this as well. Okay, let's see whether this one has the question for support settlement or not. Okay. Okay, the diagram. Internal moment means fixed member end moment. So, and this one is end cantilever. Actually, for beam analysis, we have to have the knowledge of the 3 condition. Number 1, when end is fixed. Number 2, when end is roller or pin. Number 3, when end is cantilever. Because the K as well as the distribution factor as well as the carryover factor will be different. Okay. Okay, this is for end cantilever, the diagram. Okay, then straight away move to frame. Okay, don't worry, we will continue the support settlement effect. Okay, right now. Okay, so let's look at the question back. Okay, this is the question. This is a beam, continuous beam A, B, C, D. Okay, so we have all, okay, we have like this. So now we want to consider this, okay, to reanalyze this considering support settlement. settlement. Okay, I will copy this first. Copy this first. Okay, so this is the beam. Okay, now we want to consider support settlement occurred at support B. Okay, consider at support B. Okay, of magnitude 30 mm downward. 30 mm downward. Okay. Now, when we consider support settlement, bear in mind that the beam is now has two types of fixed end moment. Okay, two types of fixed end moment. Fixed end moment, okay, can be divided into two conditions. One is fixed end moment due to external loading, and number two, fixed end moment due to delta. Okay, due to delta. Settlement is delta. Okay, so actually in the formula of fixed end moment given in appendix page 3, okay, in final exam, at the back of final exam paper, okay, the formula for fixed end moment considering delta or considering settlement or side sway is given. Okay, it is given like this. If both end is fixed like this, okay, and then due to settlement, okay, here is the delta, here is the delta. Okay, so both end is fixed, so here is A and B, here is A and B. So the delta, this one is L meter, and okay, this one is called as, this one is the original position. This one is the pin line, original position of beam. Okay, original position. Okay, the orange line. Okay, the orange line is the beam after deflection. The orange line is the beam after deflection. Okay, this is the beam after deflection or after settlement. Or after settlement. Okay, and the angle that the beam actually rotates, okay, here the beam rotates, okay, okay, the beam rotates from original position to new position, from original position to new position, and the angle is clockwise, okay. Here the angle is called as, here name chord rotation. Okay, this is the fixed end moment. This is the fixed end moment for delta. So here, okay, is the delta, Okay, the horizontal, the beam length. Okay, the member is horizontal because it is beam. Okay, what else? Okay, so the support is here. This is the support. Support fixed at A and fixed at B. And remember that for fixed support, there will be moment at support, at fixed support. And please look at this. Okay, look at this. Okay, look at this. Okay, the original position is here. Okay, due to settlement, the beam is pushed. The beam is pushed to move to this position. Okay, due to settlement, the beam is pushed to move to this position. Okay, this one, sorry, this one. Okay, it's pushed to this position. Okay, and the fixed end moment. Okay, remember that fixed end moment is the behavior. The fixed end moment is the behavior. So the beam, the moment will push back the beam to its original position. The beam, okay, the moment, the fixed end moment will push, the fixed end moment will push this point and this point, push push this beam to go back to original position, which is straight position. So the moment should be, okay, this point, at this point, to move to this, we have to apply moment in this direction. Okay, we push at that side. And at this point, okay, at A, okay, to move to its original position, we have to okay, apply moment in, okay, this direction. Okay, so that the beam, when we apply moment in same direction, then only the beam will go back to its original position. Okay, now let's look at the moment direction. Okay, this is A and this is B, right? Okay, the moment at A and the moment at B must have the same direction in order to go back to the original position of the beam. Okay, so look at the moment. Okay, it is special. If we compare to the fixed end moment for external loading, due to the bending beam, we have to apply the moment, okay, in opposite condition, so that the beam will go back to its original position, because it bend like this. Okay, bend like this, so we have to apply moment in this direction. Okay, however, for delta, for FEM due to delta or due to settlement, the moment must have in the same direction. Both must in the same direction. Okay, so how to identify in easy way, how to identify the direction of moment? How to identify the direction of moment? Okay, the easy way to identify the right direction of fixed end moments is based on the chord rotation. The chord rotation. Okay, look at this. Okay, the chord rotation will be measured from original position to new position. Okay. Okay, and original position is horizontal, because beam is horizontal member. So the datum or the original position is horizontal. The original position is horizontal. Okay, so we just we apply just like a mathematical concept. Okay, so this is represent original. Because it is straight position, it is horizontal. Then this is also represent original. Because it is straight position. Straight position. Okay, and remember the angle will be measured from original. From straight position, the angle. So, the angle is here. Okay, here is also same. Okay, do you remember this? Do you still remember this? Okay, we apply simple mathematical concept here. This is for the angle. Okay, so when the angle or chord rotation, when the angle is positive, FEM is negative. When the angle is positive, FEM is negative. So, I can conclude that for the sign of fixed end moment, due to the delta or settlement or side sway, okay, I can conclude that when, okay, chord rotation, okay, or angle is positive, fixed end moment, okay, fixed end moment, both fixed end moment, fixed end moment at A and fixed end moment at B, okay, is negative. Fixed end moment is negative. Okay, do you get the idea? Do you get the idea? So this concept is very important because we have to apply this into the determination of the member and moment, considering what? Considering support settlement. Okay, we go back to the question. Okay, consider support settlement occur at support B of magnitude 30 mm downward. 30 mm downward. Okay, now I want to show to you. I want to sketch the free body diagram for the beam after settlement. The beam after settlement. Okay, so this is the beam. Okay, here is A, B, C and D. Okay, ignore all external loading. We now want to focus on support settlement, on delta only. Okay, B is settled. B is settled means B is settled here. Okay, so A and C remain the same. There is no settlement at A and C. So this point will join with this one. And B, okay, this one is joined to this one. Okay, here is called as B prime. B prime. Okay, so here is the 30 mm or 0.03 meter, the delta. Okay. Okay, for the formula, so here the moment is like this and like this. And the formula is 6EI delta over L squared. 6EI delta over L squared. Okay. So this is the settlement. So the formula is 6ER delta over L squared. The formula is given in appendix. So this is the simple formula. The formula is the same for both sides, for both A and B, and the direction is also same for both A and B. Okay. So now, okay, using this formula, okay, for support settlement, since the FEM can be determined straight away because the delta value is known value, so we have we can calculate, okay, okay, like this, yeah. Alright. So support settlement, for support settlement, this is for support settlement. Support settlement for beam. Okay, we will analyze this. We can analyze this using two way. Okay, two way. Using two way, 1 and 2. Okay, for for number 1. Okay, A, we calculate we have table 1. Table 1 where we calculate n moment, member n moment, n moment due to loading, external loading. Okay, we calculate n moment due to external loading, and this is become the M1. Okay, and we will continue table 2. Table 2. Okay, n moment due to delta. Okay, this will become M2. So n moment final, n moment equal to M1 plus M2. Okay, this is the way number 1. Okay, we have two options. Okay, this is option number 1. Okay, since we have determined the member and moment considering external load only in the previous example, so that one will be called as M1, and we will continue to consider n moment due to delta only. Okay, and we will do the same process except the fixed n moment is different. Okay, then we will produce M2. So the answer is M1 plus M2 because when the settlement occur, the external loading is remain. Okay, is remain. Okay, we cannot remove the load. Okay, during settlement the loading is there, the settlement is there, so it is a combination. Okay, like this. Okay, option number 2. Option number 2, we can calculate FEM due to external load, and we can calculate FEM due to delta, because both FEM, okay, for both condition we can determine the value. So for option number 2, we can actually combine this FEM, and then we will solve using one table. So this okay, for option number 1 we will calculate using two tables, and the end of analysis we will combine M1 plus M2. And for second option, we combine FEM, then we will solve using one table. Solve using one table only. Okay, solve using one table only. Okay, so okay, I want to stop right now because I don't want to to produce very long video. So in the next session, I will show to you how to analyze this. I will skip manual calculation because the manual calculation have been explained in detail in my previous video. Okay, so the analysis of this, okay, I will show to you using Excel, and we will compare the result. Okay, thank you. Assalamualaikum.